Yes, you can now enter your attendance. Enter your attendance now in the chat box. Okay, let's start. So today we'll talk about call of a vector field. So when we talk about call of a vector field, uh, a vector quantity which has a spatial dependence, which is not constant. Like A is a vector which is a function of x, y, and z. That means the component of the vector here, A1 can be a function of x, y, and z, and similarly A2 can be a function of x, y, and z, and similarly A3 they can be a function of x, y, and z, right? So if A1, A2, and A3 are not constant and they are varying with space variables like x, y, and z, then this is called a vector field. So when you have a del operator operating on that vector quantity vector field with a cross product in between, that operation is called call. Okay, call of vector field. So whenever you have a cross product, like the usual cross product notation, you know that this del operator is this partial derivative with respect to x I cap, partial derivative with respect to y j cap, plus partial derivative with respect to z kk. So like the usual cross product, you will have to write I j k, and this first element del upon del x, del upon del y, del upon del z, and then a1, a2, a3. And if you do that, like if you take I here, and this is the, what is that? Shit, I forgot this term. Anyway, whatever it is, the term is, doesn't matter. So I cap coefficient will be this product, that is del a3 upon del y, and minus del a2 upon del z. So if you are having this vector operator, del operator on the left hand side, in this operation, do not write like a3 del upon del y. It's never like this. Okay. If del is the first operator, or the vector on the left hand side, the vector operator on the left hand side, this is a wrong notation. You should write it like del a3 del y. And similarly here, del a2 del z, not a2 del upon del z. It should be del a2 del upon del z. So be careful with that. And the coefficient for this j will be this and this multiply del a1 upon del z, minus this and this, you multiply del a3 upon del x. So similarly, the coefficient for k cap you can write like the usual cross product. So this is called curl of a vector field. Now, let us study this curl of a simple vector field, like this particular vector field, a vector. So again, let us draw what it is. Yeah, I think I've drawn this. Yeah, I don't think I have drawn this vector. I've drawn another vector. Minus of yi xj, yi plus xj. So you can draw this vector. Something like this. Let's say this is x, this is y, and this is, let's say, 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8, like this, for example. Now what is a vector at let's say 0 1? So at 0 1, the vector we will be having will be y is 1, y coordinate, this is x is 0, y is 1. So that means this is minus of I vector. All right. So x is 0. So at 0 1, what is 0 1? X value is 0, y value is 1. So this is the point. This is 0 1 point. At 0 1 point, what is a vector? We have a vector which is pointing along negative x-axis. So this is negative x-axis. This is positive x-axis is your I cap. This along this direction is minus of I cap. Okay. Upward direction is plus of j cap, downward direction is minus of j cap. So at this point you will have a vector having unit magnitude. I cap is unit vector, right? Having unit magnitude, but the direction is along minus of I cap. So you will have a vector like this. And at 1, 0, your A vector will be y is 0, x is 1 means j cap. So what is 1, 0? 1, 0 is this point. X coordinate value is 1, y coordinate value is 0 here at this point. So here you will have a unit vector pointing along the positive y-axis j cap direction, right? And if you are talking about, let's say, 2, 2 vector, at 2, 2 coordinates, a value will be minus of 2i, sorry, minus of 2j, y value is 2, x value is also 2, minus of 2i, sorry, minus of 2i plus of 2j. Now what is 2, 2? X coordinate 2, y coordinate 2, so the point 2, 2 is somewhere here. At this point, you have a vector along minus of 2i. What is minus of 2i? This is minus of 2i, plus of 2j, this is plus of 2j, and the resultant of this vector addition will be this. Draw a rectangle, and the diagonal of the rectangle will give you the resultant vector. And similarly, if you consider another point, minus 2, minus 3. Here, out here, your A vector will now become y is minus 3, right? Y is minus 3 means minus and minus is plus, so plus 3i plus x is minus 2, so minus of 2j. So x value minus 2, y is minus 3 means x value minus 1, minus 2. This is minus 2 coordinates, minus 1, minus 2, minus 3. This is minus 3 coordinates. So the corresponding coordinate point will be somewhere here. Here you have 3i. 3i means in this direction 1, 2, 3. Sorry, positive 3i. In this direction 1, 2, 3. So you will have 3i vector here. This is your 3i vector. You have minus of 2j. So from here, minus 1, minus 2, minus 2j. This is minus 2j. Okay. So if you look at this, addition of plus 3i cap and minus 2j vector, it will result in resultant vector like this. So if you consider all the points here, what you are going to finally have is closer to the origin, you will have small vectors, something like this, small vectors rotating, but away from the origin, you will have larger vector, something like this. Okay. If you construct all the vectors represented by the vector field. So this is what you're going to get, something like this. Okay. So towards the origin, you will have a smaller magnitude vector, which is rotating. And away from the origin, you have larger and larger vectors with larger magnitude, but also rotating, like the way I construct. If you construct all the vectors for all the coordinate points here in the space, this is what you're going to get. Now, so we can see that this vector field, A vector field, is rotating around this origin. So, sorry, this is wrong notation. I'm mistyping. So A vector, all right. So if you take a curl of A here, now, if you put a curl of A, if you remember, A vector is A1 I cap plus A2 j cap plus A3 k cap. Now you see that A1 here is minus of y, A2 here is x, and there is no coefficient for k, means A3 is 0. So you have to put all those things. Instead of A1, you just put minus y. Instead of A2, you put x. Instead of A3, you put 0. So if you do that, like if you use the Cal formula that I have written down here, if you would use the Cal formula by taking a1 as minus y and a2 as x and a3 as 0, then eventually if you calculate it correctly, this differentiation of x with respect to z is 0. Why is that? X is coordinate variables along x-axis, z is coordinate variable along z-axis. So the coordinate variables, x is independent coordinate variable, z is also independent coordinate variable. So z does not depend on x does not depend on z. They are just a coordinate variable. So the derivative here is 0. Okay. And similarly, the differentiation of y with respect to z is 0, also z 0, because y does not have any dependency on z, because y itself is an independent coordinate variable along the coordinate axis. So, but if you differentiate x with respect to x, you get 1. Differentiate y with respect to y, you get 1. Minus into minus is plus. So eventually what you are having here is plus 2k, right? So as you can see here, if you have a vector field which is rotating around in a space, the curl of that vector field is finite, or it is non-zero. The curl of the vector field is non-zero. All right. Now, if you remember, this was the vector field we construct in the previous class. That is, a vector is equal to xi plus yj. So if you remember how we constructed here, yeah, this was our vector a equal to xi plus yj. When we construct it, we find that this was a diverging field. This vector points away from the origin, and as it moves further and further away from the origin, the amplitude of the vector or the magnitude of the vector increases. Right, this was what we constructed. So this is a diverging vector field. It, as you see, this is diverging vector field. It is not rotating at all. It's not rotating at all, right? It is just spreading away from one point of origin. There is no rotation of the vector field here. So if you take a curl on such kind of vector which is not rotating like this, so here this will be your a1, here is x, your a2 here is y, a3 is again 0, because the coefficient of k cap is 0, not there, right, in this expression of this vector. So x, y, 0. So if you follow the curl formula that I have given you, so this is what you're going to get. Differentiation of y with respect to z is 0. They are independent coordinate variables, so they are 0. And this is also 0. All of them are 0. And eventually you see that this is 0. So that means non-rotating vector field. Curl of non-rotating vector field. Curl of non-rotating vector field is always 0. If the vector field is not rotating, if the vector field is just a straight line, or if the vector field is not rotation, this will be 0. Right. So where is another example? We have given you another example over here, right? This was an example. The vector we consider here is a vector is equal to 1j. A vector equal to 1j. Let us take the curl of that vector. Wait, let me show you. Let me here. If you look at this, a vector equal to 1j, this is also non-rotating. As you see, this vector is just pointing towards the positive y-axis, right? All the vector fields represented by this vector is pointing towards the positive y-axis. There is no rotation of this vector. They are just pointing along the same direction. All the vector fields are traveling along the same direction. So if they are traveling along the same direction without any rotation, let's see what we get if we take a curl of that. So if I take a curl of this, a vector is equal to 1j. What I'm going to have here is that curl of a will be I, j, k, del upon del x, del upon del y, del upon del z, and there is no I term here, I cap term here, so the coefficient of I cap is 0. The coefficient of j cap is 1. The coefficient of k cap is also 0 out here. So if you do that, this will be I cap into this product is 0 minus this into this del 1 upon del z plus j cap in coefficient will be j cap this into this product is 0, del upon del x into 0 is 0, plus k cap uh, k cap coefficient will be del 1 upon del x minus 0. So this is constant. Differentiation of 1 with respect to z is 0. Differentiation of 1 with respect to x is also 0. So all the terms will be 0. So that means if you have vector fields which are pointing along the same direction, like the positive y-axis in this particular example, without any rotation, then the curl is 0, right? And similarly over here, diverging vector field, we have the curl is 0. Only when we have a rotation of the vector field, then we see that the curl is non-zero in this case, in this particular example. So what is the physical meaning of a curl of vector field? So when you perform this curl operation on a vector field, what does that mean, right? So you can see that by now, I think everybody now understands that curl of a vector field is a measure of the rotation of the vector field. Okay, if the vector field is non-rotating, then it is 0. If the vector field is rotating, then it is non-zero. And depending on the rotation of the vector field, curl of that vector field will give you different values. If the curl of the vector field is quite large, then the vector you're representing is like a rotating vector field. In static charge distribution, like that the electric lines of force are always a straight line. Okay, so like for example, if you have positive charge here, static charge distribution means charge is stationary. If you consider stationary charge particle, in a stationary charge particle, the electric lines of force are pointing, diverging like this. The electric lines of force are diverging away like this in stationary charge distribution. Or if it is a mass of q, then the electric lines of force are pointing towards the negative charge. The electric lines of force are pointing towards the negative charge. So the electric field at any point is tangent to the electric lines of force. All right. So in this case, the electric lines of force are also, electric field is also a straight line. Electric lines of force are pointing towards negative charge in stationary charge distribution, and here also pointing away from that. And at every point here, the electric field is tangent to the lines of force. So the electric fields are also converging here in this case, and here is this diverging. There is no rotation of the electric field here, right? So because of that, in static charge distribution, the curl of electric field is 0. Curl of electric field is 0. But later on, you will find that when we have a moving charge, non-static charge, when you have a moving charge, like in the case of electromagnetic induction, Faraday's law, you will find that curl of electric field is non-zero. Actually, according to Faraday's law, curl of electric field is minus of del B upon del T. Okay, this is the differential form of Faraday's law. In that case, Faraday's law is a case in which you have a non-static moving charge. All right. So on the other hand, magnetic lines of force originate at North Pole and terminate at South Pole, and there is a rotation, as you have seen already here. Where is that? Yeah, over here. Magnetic lines of force is rotating field, right? In this rotating field, there is a rotation, means curl of B is non-zero. Curl of B is non-zero, and there is this fundamental law on magnetism called Ampere's law. I think everybody is aware of Ampere's law. Ampere's law in differential form is actually curl of B is equal to mu J vector. J is the current density, mu is the permeability of the medium. This is Ampere's law in differential form. Okay, so since the magnetic lines of force, the magnetic poles always exist in pair, and one from North Pole it originates and rotating around and converging at South Pole again. Therefore, it's a rotating field, right? Magnetic field is. So curl of B is non-zero, and the quantity that is curl of B is given by Ampere's law, which is mu into J vector. Current density, J vector, and permeability of the medium mu. So I hope you know what we mean by this curl of a vector field now. So these are some like simple vector algebra. This is something which you have to practice yourself also. So here this is ln. Ln means natural logarithm. Natural logarithm. So whenever you write ln means it is equivalent to log to the base e, natural log, right? So r is the position vector in space, like I discussed before. R is a position vector in space. It can represent the location of it can represent the location of a point in the space. This is x exists, y exists, z exists. So any point in the space, the position of that point, the vector pointing, the vector defining the position of that point is what we know it as a r vector. So what is r vector? R vector is, if you drop a perpendicular here, the coefficient of the x coordinate is x, the coefficient along the y coordinate value is, let's say, y, and the coefficient along the z coordinates is, let's say, this is z, right? So therefore your r vector is xi plus yj plus zk cap, right? So whenever you take a magnitude, so when you simply write r without any vector, that is representing the magnitude of the vector r. Magnitude of the vector r is square root of x square plus y square plus z square. Okay, without this unit vectors. When you take the magnitude, square root of the coefficient x square, y square, and z square. Like if you have a vector a1, a here, a1 I cap plus a2 j cap plus a3 k cap. If you are going to take the magnitude of the magnitude of the vector is simply square root of a1 square plus a2 square plus a3 square. So I think everybody knows already. So that's how we take the magnitude. So when you take the magnitude, this is what you get, and this is simply to the power 1 upon 2. So ln natural log, if you take a log of this thing, ln of this thing, this will be, you know that ln of e to the power x is x into ln of e, right? Or ln of a to the power 2 will be 2 ln of a. So I hope you know this logarithm formula. So if you take a if you look at this ln of this vector, magnitude of this r vector will be scalar. This quantity is scalar, right? This quantity is scalar. There is no vector sign here. This quantity is scalar. So you take the gradient on that, gradient of the scalar quantity. So this is the del operator operating on this scalar quantity. Now this scalar quantity, you will have to multiply with this thing. That means differentiation of this scalar quantity with respect to x, differentiation of the same quantity with respect to y and z. So you just perform the differentiation. So I think I don't need to revise all this calculus. So I think everybody knows that differentiation of ln of x cube will be something like this. Differentiation with respect to x means 1 upon x cube into differentiation of x cube with respect to x. So this will be 1 upon x cube into 3x square. So I hope you know this. So if you do that, differentiation of ln of this would be 1 upon this, and then differentiation of this quantity will be differentiation of y square and z squares are with respect to x are 0. Differentiation of x square with respect to x is 2x. So if you follow that simple calculus, then finally this is what you get. This is your vector itself, and this is your r square, because your r is square root of this. So x square plus y square plus z square will be your r square. So I think you should be able to follow this if you are familiar with this kind of calculus, but you are expected to know the calculus, right? So this is also something similar. Just a minute, I need to mute for 1 minute.